Okay, so the good news is chapter 8 is a very different set of topics from what we've been doing. I mean, really, chapter 8 stands alone. You could actually teach a small mini course on chapter 8. There's so much amazing stuff in there, and stuff you've never thought of before, I'm sure. Okay, in this chapter, we're going to encounter new coordinate systems, imaginary numbers being graphed and analyzed. We're going to learn to find a cube root of things like I. We're also going to study vectors from two-dimensional standpoint and three-dimensional standpoint. So we'll do our first 3D map this year.
Is this an important chapter for calculus?
Some of it. That's a good question. Some of it is important for PC calculus. Some of it is not important. And just basically a whole slew of new concepts and ideas. Okay, so we're going to start very, very simple. And I'm going to start with just a real-life example of what polar coordinates are. Okay? And I know for a fact you're going to understand this. Okay? You have all the background you need for this. Okay, so let's say that you were asked to find the distance between your home and the school. Okay? So let's say that, let's just say that you're given the following picture, and the school on an XY plane is located at 3, 4. So we'll label this VP for Villa Park. And I know that this particular area of the city isn't really laid out that much in blocks. You know, it's kind of, some blocks are big and some blocks are small. But imagine if this was just sort of a standard city and everything was, you know, 1 block wide, 1 block long, and, you know, just streets everywhere like a grid. And you lived right here at the origin. And you wanted to find the distance from your house to Villa Park. Right? How would you find that distance? I'm asking basically for this distance. How would you get that distance? Distance formula, that'll work. Pythagorean theorem, which is really where the distance formula is from. Yeah. Yeah, that'll work. And so you could construct like a little right triangle here, do Pythagorean theorem, or you could bust out the distance formula. In any case, what is the distance from the home to Villa Park here? 5, correct. Okay? All right. Now, if I told you that Villa Park is at 3, 4, this gives us the location of Villa Park in rectangular coordinates, it's called. These are the rectangular coordinates of VP. Okay? Rectangular coordinates. Why are they rectangular coordinates? It's because when these were invented by the guy, or the guy who gets most credit for this is Descartes, so we call it a Cartesian plane. The reason it's considered rectangular is because you're traveling in a right angle fashion. Rectangle literally means right angle. So you're going, you know, rights and lefts, ups and downs, you know, and everything's kind of rectangular motion. So that's called rectangular coordinates. And we all know what 3, 4 means, right? The thing about it, though, is if you were in a helicopter flying from home to Villa Park, you would not fly 3 units east and 4 units north. You wouldn't do that. You'd probably just fly in a straight shot to the school, right? So another way to describe where Villa Park is at is to say this. Villa Park is 5 blocks from home. Does that describe the location of Villa Park? If I told you I lived 3 miles from school, would you know where I lived? Or if I told you Villa Park was 3 miles from my home, would you be able to find Villa Park from my home?
If you make a circle, that's fine.
Yeah, this is not enough information. Right. It's not enough information to find Villa Park, but it's a start, right? So if I said I live 5 blocks from VP, you wouldn't know everything about like where VP is, but you would at least know that it's somewhere on this circle. What more information, what other information would need to be given in order to not use the 3 and 4, but to know how to go from my home to Villa Park? Like what other fact would you need to know? Not just how far you have to go, but which, what? Okay, so you definitely need 2 numbers in 2 dimensions to find a location. That is a fact. Okay, in any coordinate system, no matter how you like to measure, if you want to find a point in 2D, you need two numbers. There's no exceptions. Okay? If you're in 3 dimensions, you have to have 3 numbers in order to find anything. And they cannot be redundant numbers. They have to be all very helpful. Okay? But in this particular case, you would definitely need to know the angle of travel. So you can't just say, I live 5 miles from school, and then from there everybody can figure out where the school is. No, you need to give me the angle. So what I'm saying is, another way of saying where Villa Park is to say it is 5 blocks from home and along the angle, what? What angle is this? Well, we typically measure using standard position reference frame. Remember, we used to measure angles all the time in this class. I would like to know this angle, so I'm going to pause for a minute and see if you can find it. That's why you need your calculator. Take a moment and give me that angle. Okay? Don't shout it out. Write it down. Okay? Make sure your calculator's in degrees mode. Just for today, for this real life example, we will use lots of radians, but let's just use degrees right this minute. Degrees mode, see if you can get that angle. Don't forget about SOHCAHTOA. Always and forever true on the right triangle. I think you know adjacent, hypotenuse, and opposite. So you can use any trig function you like. You can use sine, you can use cosine, you can use tangent. Pick one. Sine, cosine, tangent. Use one. Okay. Did anyone get an angle? You can shout it out. Eddie?
53.13 degrees.
Okay. 53. And we're going to, starting this semester, we're going to do nearest thousandth on every calculator measurement we do. No exceptions and no forgiveness. Okay, I have to get you totally trained for the AP exam next year. Most of you will be taking calculus. So nearest thousandth, no exceptions, no forgiveness. 3 digits after every decimal point, or I mark it wrong. Okay? 53.130. Is that believable? Looking at the picture, do you think the calculator gave us the right answer? Probably. Right? I mean, this is 0 degrees and this is 90, so I can totally imagine that being 53 degrees, roughly, right? Okay, so which is better, to say that Villa Park is at the Cartesian or rectangular coordinates 3, 4, or to say that Villa Park is 5 miles from home in the direction 53.130? Which is the better way? They're exactly the same. Okay, they're equally valid ways of locating a point. Okay, so our philosophy in this chapter is going to change a little bit. Instead of always giving x and y, we're going to start talking about what would happen if they gave us the distance to the origin and the angle to the standard position. Okay? All right. So here's how we would write our newly found facts. Okay? We would write it this way. VP is at 5, 53.130 degrees. Okay? What I'm giving you here is r, the distance from the origin, and theta, the angle in standard position. We've used r and theta before. They have not changed meaning. Okay? All right. These are called the polar coordinates. These are the new word here, polar coordinates. And I have 6 minutes left to give you a couple handy little formulas that will help you convert from x and y to r and theta, and from r and theta to x and y. And that's all I want to do. Okay? So this won't take very long, but this is about how much time I have left. So this will be our first video and very short. Okay, so here's the basic idea. All right? If you're given a point at x and y, so if you have x and y, you can get r and theta by using these two formulas. r is supposed to be the distance to the origin. So r should just simply be the square root of x squared plus y squared. Now the next lesson in this section, I will mention that r can be negative now. Okay? But we'll talk about that when it arises. The first thing you'll need to find is the distance to the origin, and that is found by r equals x squared plus y squared square root. So you'll definitely need this formula.
Is it r
R squared is x squared plus y squared, but r would be the square root of x squared plus y squared. Okay? That's just Pythagorean theorem, is all it is. Okay? To find theta, the safest thing to do is to use the x and y you were given. So tangent's really the best choice. See? You don't want to use r if you just found r. You want to use the x and y you were given. So theta is inverse tan of y over x. Now there is a slight disclaimer on this second formula. Okay? So grab your calculator with me and just try this real quick. Let's say you were at the point negative 3, 4. The distance to the origin, of course, is still 5. But what does the calculator say the angle is? Because I'm not sure we should trust it. Let's try it real quick. Everybody get your calculator out and type in inverse tan of 4 over negative 3. Because I don't believe the answer. Let's try it. This brings up a little twist. So you got to be careful with calculators sometimes. Everybody go and type that out. Make sure your degrees mode. Type, type, type. What is the calculator saying? Yeah, the calculator can just factor out the negative. It's an odd function. This is the opposite of the answer we had last time. Negative 53.130 degrees. I don't believe that answer. Why don't I believe that answer?
Because you can't have a quadrant 4.
Yeah, that's a quadrant 4 angle, right? That represents down here. And that's not where my point is. So I think the calculator's lying to me. Why is the calculator lying to me?
Inverse tan can only be between quadrant 1 and 4.
Right. When you change a statement like tan equals y over x into theta equals inverse tan of y over x, there are actually an infinite number of answers to the first equation, but this one has one answer and it has to be from quadrants 1 and 4. We talked about range of answers. So the calculator is just trying to obey the rules, and it's given us a quadrant 4 angle, which we can't trust. So if the calculator gives us the answer to be here, how can we correct it to get the right answer? Add 180, correct. So I'm going to put a little plus 180 here. Now, will the calculator sometimes tell me the truth? Yes. The calculator will tell you the truth if your point is in quadrant 1 or 4. It will lie to you if your point is in quadrants 2 or 3. See? And therefore, the rule is this. You'll add 180 if x is negative. Quadrants 2 and 3. So that's the caveat, or the little twist to this formula. You only add the 180 if x is negative. So hang on to these formulas, and we'll use them a lot. Okay? Okay, so we can see we have two formulas, one for finding r when we know x and y, and one for finding theta when we know x and y. The second one's conditional. It depends on the x value you're given. So let's try a quick example of it. Let's say that you're asked to find the polar coordinates of, and let's make it a multi-part one. Okay, so let's find the coordinates of the point negative 3, 0. The next one will be negative 2, 3. And let's try 4, 5. Okay, so the goal is to, if you want to plot them, you can, but the goal is basically to find the r and the theta value. Okay, sometimes just drawing it is enough. For example, the point negative 3, 0, you can tell how far it is from the origin. It's 3 spaces from the origin. Why would you use a formula for that? So we already know the distance is 3. Also, you can tell where the angle is. It's over on the left side of the x-axis. This is at 180. So why use a formula for something like that? So that one's done. The next one, well, we might need the formulas. So r is going to be the square root of 4 plus 9. That's just x squared plus y squared. In other words, root 13. The theta is going to be inverse tan of 3 over negative 2. And we will be adding 180. Notice that the x coordinate is negative on this problem. Okay, and we'll go ahead and keep it in degrees. We'll switch to radians in about a day and a half, and we'll be sure to use radians as often as possible. Okay, so the correct distance in the origin is rad 13, or you can just use the decimal equivalent, which is 3.606, rounded to the nearest thousandth, and the angle is inverse tan of negative 1.5, that's 3 over negative 2, and in degrees that is, hold on, sorry about that, I have my calculator in radian mode. Okay, so the calculator is saying negative 56.309. I don't believe it. I'm going to add that 180. I'm doing this again because the x is negative. All right, so my answer is 123.7. I'm supposed to use nearest thousandth. Kind of run out of room here. Let me move some things down a little bit. Need some more space. All right. So 123 point, and my calculator is already rounding it to the nearest hundredth, so I'm going to go ahead and put a 0 at the end for nearest thousandth. This is degrees, so I want to go ahead and indicate that using the degrees symbol on my answer. So don't forget the degrees symbol. All right. There it is. Okay, and then the last one, notice the r is going to be the square root of basically 16 plus 25, so that's the square root of 41. That's exactly the square root of 41. As a decimal, that's 6.403. The angle is inverse tan of 5/4. And should I add 180 or not? Will the calculator lie to me? No, the calculator will not lie to me. This point is in quadrant 1, and the range of tan includes both quadrants 1 and 4. So whatever the calculator says, I can fully trust. And it's 51.340 degrees. So the correct polar coordinates for this problem are, I'll write the answer in purple, 6.403, or it's even more accurate to write rad 41, comma, 51.340 degrees. Those are the polar coordinates. Now don't be surprised if the textbook gives answers in radians. Okay? So that can happen. Let's go on and look at a separate situation. Let's say that you actually had r and theta. So you knew r, and you knew the angle theta, but you wanted x and y. How would you do that? So let's go ahead and take that situation. So if you have r and theta, and you need x and y, you can use the following. Now keep in mind what you're trying to do. This is not complicated. You've got x here and y here. In other words, you're looking for adjacent and opposite. And you know hypotenuse and the angles. So probably the best choices here are cosine and sine. Okay, so basically we can write down the fact that cos theta is x over r. Nothing wrong with that statement. That's just SOHCAHTOA's, the cos statement. And this means that we can find x by simply multiplying r with cosine theta. And we also know that sine theta is opposite of hypotenuse. In this case, in quadrant 1, it's just y over r. It's also sine is y over r, something else we memorized earlier in the year. And we can then find y by multiplying r against sine theta. Okay, so let's do a quick example of how we might find the Cartesian or rectangular coordinates given polar coordinates. So example 2. Convert the following points to rectangular coordinates that means you have r and theta, you'll need x and y. Okay, so the first one is the point 5, 25 degrees. The second one is 3, 270. And the next one is, let's just make an interesting one. How about, let's do 5 units from the origin, and let's do 237. So this is in quadrant 3. All right. Let's go ahead and use the formula. This is very, very simple. It's also very straightforward compared to the last example we did because there really is no twists or turns anywhere. You can literally just do 5 cos 25, 5 sine 25. And this should do it. This should give you the correct coordinates first try. So 5 cos 25 is 4.531. All right. Sorry, I'm just typing here. Sorry for that. And then I need 5 sine 25. And that's 2.113. And that's the end of it. Those are the x and y coordinates. Notice that when the Cartesian, when the polar numbers are nice, we get these awkward x and y, and the opposite's true. You know, if you have a nice r and x and y, you might not get a very decent looking r and theta, but that's okay. We don't mind these decimals at all, right? Okay, let's look at this next one. 3 cos 270. Oops, there's no need for a comma there. 3 cos 270, comma, 3 sine 270. Now this one you don't really need a calculator for because you know that cosine 270 is 0 and sine 270 is negative 1. But you're welcome to use a calculator if you need, as long as you're still familiar with your unit circle. And then this last one, move this down a little bit. There we go. This last one is going to be, of course, 5 cos 237, 5 sine 237, and we'll type that in. And this just gave me negative 2.723, comma, negative 4.193, like that. Okay, now I just want to point something out. All of these have, of course, meaning. So the first one is saying, I'm thinking of a point that is 5 units from the origin at an angle 25. In other words, the point is here, somewhere on the, I guess you could say, if these were like circles of radius 1, 2, 3, 4, 5, and this is 0 degrees and this is 90, 5 units away from the origin, that'd be out here on the 5th circle, at 25 degrees, that's our point, right? And if you look at the answer in Cartesian coordinates or rectangular coordinates, we got 4.531, 2.113. If you look closely, you can see that that does make perfect sense. This is out here between 1, 2, 3, 4, and 5. It's right there between 4 and 5. See? And in the y sense, we have 1, 2, 3. It's right up here between 2 and 3. So this point, this big purple point I just drew, really does have both descriptions accurate. The next one also makes sense. So it's kind of nice to draw a picture for these. 3, 270 would mean 3 units from the origin. So you could think of that as somewhere along this third circle, see? But down at the 270 angle. So 270 is this angle specifically at the bottom. So it creates just this blue point, see? And if you look at this from a Cartesian perspective, where this is x and y, of course this is the point -3. It's down 3 spaces, right below the origin, okay? And this next one, we don't have to plot the whole thing, but you can tell this is a quadrant 3 angle. And notice the double negative on these. Pretty believable. The double negative shows us it's quadrant 3, so we can trust that answer. So actually we do trust our calculator very much so when we're doing polar to rectangular. It's when we go backwards we have to be careful. So I just want to remind you, back in this example, we had to be a little bit careful not to trust the calculator when it gives us a theta. Okay? All right. Now let's just talk about the fact that every point r theta has multiple names. Okay, so this just goes back to an old idea of coterminality. That's a really horrible drawing, sorry about that. But let's say that you had the point right here, and it was 3 circles out, and we're at 150. Okay, that means that we are on the 3rd ring outward at the angle 150, so that's in quadrant 2. This is not the only correct name for this point. 3, 150 can also be called 3, 510. Why? Because 510 is coterminal with 150. What did I just do? I just added 360 right here, which brought me another cycle around. See? So basically 510 and 150 are coterminal. Adding 360 puts me right back in the same location. So let me ask you this, is point P's coordinates 3, 150, or is point P's coordinates 3, 510? The answer is it doesn't matter. You can call it either one. They're exactly the same point. Interesting. Now what are the Cartesian or rectangular coordinates of this point? Well, it doesn't matter which one you choose, 3, 150 degrees or 3, 510 degrees. Either way you think of it, the x and y are the same. So if you take 3 cos 150 and 3 sine 150, or 3 cos 510, 3 sine 510, it doesn't matter. Either way you're going to get negative 2.598, comma 1.500. So 1.50, I'll write that again down here, a little hard to read. Negative 2.598, 1.500. In other words, a point in space on a rectangular plane, like on a two-dimensional plane, has exactly one rectangular coordinates description. So rectangular coordinates, I should say points, have one rectangular coordinate description. So points have unique rectangular coordinates, you could say. One of a kind. Only one rectangular coordinate description. But we've already seen that point P in the polar world has multiple names. We've already said that it has 3, 150. We said that it has 3, 510 as a name. They're exactly the same point. Can you think of others? So you should pause the video and play around with this. What other ways could you describe it? Okay, hopefully you paused it. What about 3, negative 210. That's the same exact position. It's just more going backwards 210 degrees. That still lands you right at 150, doesn't it? Okay, so one that you may not have thought of is this one. Negative 3, comma, negative 30. Negative 3, comma, negative 30. If you think you might know why I'm allowing this name, I'll let you pause the video and think about it. I'm going to go on and explain why I think this is also a good name for that point P up above. Okay, so the point is over here on the third ring at 150, right? But one way to get there is to actually go to negative 30, which is over here, negative 30 degrees. And then, instead of traveling in that direction, travel backwards out here to point P. Okay, so I'll say that again. Let me draw that again real quick. I'll say it even a different way. We know that 150 is over here, which of course is the exact opposite, diametrically opposed to negative 30, or you could call this 330 over here. See? So those are opposite directions. If we say, let's say you were standing here at the origin and you wanted to get to point P, you could face, look this direction towards negative 30, and then walk backwards to this point. So walk backwards that way. Or you could do it the other way, where you face point P and just walk directly towards it. Okay, so I'll try to draw that. This is kind of hard to draw, but third circle. If you're here, looking at negative 30, to get to point P, which is on the other side, you'd have to walk backwards. See? And so your R would be negative. So you'd walk backwards. So you're looking to the negative 30, but you're walking backwards, see? So that's why I'm allowing this to be called negative 3, negative 30. You're aiming at your body at negative 30, but you're walking backwards. Or, of course, you could just face point P and walk towards it, which provides some of these other descriptions up here. Okay? Alright, so actually there are not just 4 names for this point, there's an infinite number of names. So we have coterminality, which already gives us an infinite number of ways to name the point. And we have this idea of walking backwards, which just makes it all the more dense in answer choices. Okay, so here are basically your options. You can go forward, walking forward, you could let your R be positive, and then you could use the theta plus any 2 pi amount you wish. Okay? So you can basically add 360k. I'll use degrees. We'll put 360 here for today. Okay? So this will give you possible names. And if you decide to walk backwards, you could basically add multiples of 180. So you could do like plus or minus 180. Okay? Or you could add 540. Alright, so to summarize all of this, we'll go ahead and put a k on both of these, and we'll say that k is even. K is even. So k is an even number in both cases. Excuse me, k is even on the first one, k is odd on the second one. That way, you'll always be going to the right point. Okay, if this is kind of confusing for you, it shouldn't be. The idea is you should be able to draw the point and find an infinite number of ways to sort of describe the angle. And if you're allowing walking backwards, you can even add 180 to the angle, or 540, that sort of thing. And we'll get some practice on this in the homework, of course. And that's good enough for today.